Today I would like to try and close for the moment the part on link analysis. Okay? By the way, did you find on the website there are new notes about personalized PageRank? If you find any mistakes, it's possible. I mean, just notify me so that I can fix them. Okay? That should not be, but you never know. Maybe a typo or something. So today I want to address a couple of things, if I have time. The first one is this issue, and the second one is this one. So first of all, in PageRank, we have a single measure of importance, one score for everybody. Yeah? But as we have seen, this, in a way, this in some sense establishes a key difference between pages like this and like this. So this will tend to be more important, whereas this will normally get less importance. Of course, everything depends on the incoming links, which we don't know here, right? But everything else being equal, this page will be more important than this. Is this always correct? If you apply PageRank, that's the way it is, and the reason is that there is no distinction in roles. For example, if I have a page that maybe has not so high a PageRank value, but it points to authoritative pages. You see my point? So I have a page that maybe it's a blog. I mean, well, a blog can have many incoming links. Well, let's say, I don't know, it is some private blog, not so well known, but it might still have high quality links pointing to authoritative pages for certain topics of interest. Okay? So I would like to actually also keep these into account. So for example, pages pointing to high quality information sources. I cannot do this directly with PageRank unless the pages themselves are already authoritative. Okay? Is there a way to take this into account? This is the first thing we are going to look at. So, actually, at the very same time of PageRank, another paper was written. It was called Authorities and Hubs in Hyperlinked Environment, or something like that. Detecting Authorities and Hubs in Hyperlinked Environments. It was written by John Kleinberg. He's a strong guy in data science. He is very much committed with social network analysis and so on. And he was, at the very same time of bringing Page, essentially proposed an alternative way to rank pages in the web. The most prominent idea, the most prominent difference between the algorithm proposed by Kleinberg and PageRank is that actually it accounts, let's say, it accounts for both incoming and outgoing edge links. So trying to distinguish between two different roles that a page can have, which is being authoritative for some reason or pointing to authoritative sources. Okay, so if you think about this is a matter of role. So for example, I may want to have an expert on something, so in this case an authoritative page, or I want to have an expert who knows whom I should ask for something. You know the difference? Actually, both these aspects can be relevant, and the idea of Kleinberg's algorithm was to keep both aspects into account. So, for example, assume that we want to find good newspapers. If you apply PageRank, you'll get good newspapers. whatever good means, authoritative and so important newspapers. With Kleinberg's algorithm, you do not just find good newspapers, you also find pages or people that in a sort of coordinated way point to good newspapers. In a way, you're measuring the basin of influence of these pages. In a way, you're tracking the nodes that most contribute to the importance, to the authority of newspaper pages. And the idea is always the same. Every link is a vote. But this time, it is not just important who receives the vote, but also who gives the vote. In a nutshell, I am important if I am pointed to from good pages, and I'm a good page if I point to authoritative pages. You see? It's a self-reinforcing relationship once again. Just in this way, in this perspective, every page in a web graph will have two scores. One is called the hub score, and it measures to which extent the page you are considering points to good pages, to authoritative pages. And another one will be the authority score, which is something related to PageRank. Okay? It is not exactly PageRank because it's computed in a different way, but it is related to PageRank. Let's say that if you consider Pearson's correlation coefficient between authority scores and PageRank, normally they will be highly correlated. But on top of that, you also have a hubness score, which measures to which extent every page points to authoritative pages. Okay? And how are you going to compute this? Well, actually, it is not very different from PageRank. I mean, the underlying principle is a self-reinforcing relationship. Let me see. So, before I give you an idea of what it means to compute hubs and authorities, let me just tell you what in our mind a hub and an authority should be. Let's say that an authority is essentially something that would be considered an authoritative page according to PageRank definition. So it is a page that in some way is often on your way. If you take a random walk, you will encounter this page pretty often, more often than other pages. So in that case, if you're looking for newspapers, then authorities will be, I don't know, newspaper homepages. If you're looking for teaching for classes in a university on a given topic, this could be course homepages. If you're interested in cars, let's say an authoritative page, an authority could be car manufacturer web pages, and so on. Is that clear? So whatever you expect to find on the top of your results list, if you issue a query on those topics in Google, basically. What is a hub? A hub is actually a page that points to authorities. For example, if you have a list of newspaper web pages, that will be a hub. If you have, so for each of these categories, you can have some notion of a related hub, a course bulletin, so a list of links to course homepages, a list of US of manufacturers, car manufacturers, and so on. Okay? That's the difference. So sometimes these pages are also authorities and vice versa. Sometimes that needs not be the case. Okay? Not necessarily. Now, how could I intuitively try to compute hubness and authorities in a self-reinforcing way, following an idea of iterative improvement, computation like we did for PageRank? Let's try with an example. And let's see where this takes us, okay? So, this is a very simple case. Actually, it's a very simple case because the graph you have is a bipartite graph, right? So, in reality, you have not a bipartite graph. But let's put it this way. This could be the ideal solution, the ideal situation that in some way triggered the idea of proposing the algorithm I'm about to show you in Kleinberg's mind. So assume that you have, for example, authorities with respect, I don't know, news or whatever. Let's say authoritative pages. This will be authoritative if you want to do online shopping. This is authoritative if you want to find a good search engine and so on. Then you will have pages pointing to this. For the moment, we are assuming that you have not, links only go from one end to the other of this bipartite graph, just to simplify. What can you do in this case? You could begin in a stupid way in the following way. Let's begin with authorities. So, Amazon has an initial authority score 3. It gets 3 votes. Facebook also gets 3, Yahoo gets 3 votes, Facebook gets 1 vote, and so on, okay? So you could just have a first round of votes. This will define a first authority vector in which some pages are more important than the others. But this is just one step. How can I take further steps? I could argue in a way, I could think similarly to what we did with PageRank in the following way. In PageRank we said a page has a high PageRank when it is pointed from pages that have a high PageRank, right? So in this case we could say a hub has a higher hubness score when it points to higher authority pages. You see my point? For example, I could say, well, this guy here actually is pointing to Amazon, which has 3 votes, which received 3 votes. Let's see. Maybe it could be a bit more important than this guy. I don't know. If the total number of votes for the pages this guy points to is less. Okay? Let me see another iteration and this will be clear. So, essentially, I could do the following. I could use the links of the hubs to give initial scores to the authorities and then send these scores back to the originating page. Notice the following, that what is happening here is that actually the hubness score that this guy receives depends on the number of points linking to each authority the guy points to. So this is getting a 3 because it's pointing to Amazon. Likewise, this one. This guy is getting a 6 because it is linking to Yahoo that got 3 votes in the previous iteration and to Amazon that equally got 3 votes. So for a total of 6. You get the idea? Of course, what can I do? I mean, it's a nice game. Let's keep it going. Yeah? So I propagate back. Now, what is the new score of Yahoo? It is 6 plus 3 plus 6, 15, and so on. If I keep going on like this, you will get 2 vectors over time. One is the aggregate vector of scores, and the other one is the aggregate vector of hubs. So it should be clear that a real graph is not like this. It's a bipartite graph. For example, if I wanted to compute the authority of this page, that would be 0. Trivially, because there is no page pointing to this, right? It can never be other than 0. But in a real graph, the picture will not be like this. So you will have links going everywhere, Maybe this page has no incoming link, which means it is not getting any authority, but maybe it has just one incoming link, which through some path is connected to the high authority page. In that case, it will eventually get some score, some authority score. Okay? So, what is happening with this? Does it make sense, first of all? Does something like this make sense at all? Well, apparently, it does make some sense. And one way to uncover this is to, first of all, try and ask, is there any mathematical meaning to this? So does it mean anything mathematically speaking? Okay? Did you get it so far? It's not hard, right? Ping pong. Yeah, it's a ping pong. So, can we give a mathematical formulation of this way of computing the scores? What do you think?
Well, the score of an app is basically the in degree of the node it points to.
Sorry?
The score of the app is the in degree of the node.
Yeah, well, it's more than the in degree. You see, it's
right.
It's the weighted.
Degree, yes.
It's iterated. It's a bit more complicated. So the first time, you're right. I will get. Consider this page, for example. It is not just the in degree. It's the sum of the in degrees of the pages. The page points to. It's a bit more complicated than that. But is it really complicated? Whenever you want to make a sense of it, you can ask the following question. Assume that at some point I have a vector of hubs. I have computed a vector of hubs. Okay? At the end of some step, I have computed a vector of hubs. For example, the end of the first step. So one step is 2 iterations. First iteration, second iteration, okay? What is the new value of the hub in the next iteration? We have to compute it, right? So, if this points to this, I get the authority value of this page, right? Let's try to write this. So this is the vector x, the vector h. Let us call x the component that corresponds to page x. For example, 3, not 3. Let's say this node in this example, or this node here. Let us see how it is computed. Yeah? You take all the links that, you take all the pages that X points to, and you sum the authority scores. Is that right? Check on that page, on that slide. Is it correct? Yeah? Let's say the two vectors are H and A. A stands for authority, H stands for hub. Is that correct? Yes or no? Now, look at this sum. What is this sum? A, X, Y. 1 if this link exists, 0 otherwise. You agree? What does it look like? This is an adjacency matrix, right? It is the adjacency matrix of the graph. So, where this stands for the row X of the matrix times the hub, the authority vector. Okay? Is that clear? So, oh, interesting. What happens for the authorities? So now A is the adjacency matrix of the graph. If the graph were weighted for some reason, you have weights on the links. Why weights? I don't know. Maybe these are just websites and you put a weight that is the number of links from this website to this other website. Okay? In that case, you have a weight. But here, nothing changes. It is the same. So, how do I want? Well, what is the authority for this page? Well, the authority for this page, in this case, these pages have no authority because they have no incoming links. But if they had, well, then you should have to compute the following. Right? Nope. Yeah? So, just a sec, I don't want to make mistakes. No, it is correct like this. They're all the ones pointing to X. Yes. Okay. I take the column of the matrix, I take column X of matrix A. Now this is the column. Okay. This is the row of the matrix, row X. So just to be clear, before I was considering this when computing the hubs, the new hub scores. Now I'm considering this, the column. Since this is a column vector, I have to transpose. Okay? And then I get this. Why do I get this? Let us look at this equation. This equation says the following, that I should consider all links that point to X. and sum their hubs. Where are the links that point to X? They are on this column. You see that? Yeah? Do you agree with me? No? I can take a further step. Well, actually, this is the step. Huh? Actually, this is the step. So here a star means that the second component or the first component in this case varies along all possible rows or columns. Okay, so this index varies in all possible ways and the other stays fixed. That is the meaning of this. You see here in this sum, the rows are moving, X is fixed. Okay? And it corresponds, you should convince yourselves only of the following equality. This is the same as this. Is this correct? All the pages that are pointing to X, where are these pages? They are here. Whenever there is a 1, I have a page that is pointing to X. In this other case, where are the pages that are pointed from X? They are here. Okay? You just sit there, you think a little bit, and you will get to this. So in one case, you have the matrix. In another case, you have the transposed of the matrix. Okay? Of course, I've written this for a single entry. I can write this for the entire vector. And then I will get two equations that are the following. Can I cancel this out? Yes.
The column is X or Y?
The column is X.
Why?
Because I'm computing the, for every page, X, I can compute a hubness score and an authority score. When I want to compute the hubness score, I'm looking at the row of X. When I want to compute the authority score, I'm looking at the column. It is just in the equation. It is just a definition.
Yes, but why in the matrix?
This year?
No.
There's two times, there's X on the rows and X on the columns.
X.
Yeah, this was just to show you that every matrix is a square matrix. So it has a row X and it has a column X, right? The row X tells me...
Because it is transformed.
No, because it's an adjacency matrix. Every adjacency matrix for every node has one column that corresponds to the node and one row that corresponds to that node. Is it clear why? I mean, in an adjacency matrix, you have a 1. Well, then here you have a 1 only if you have a self loop, if you're pointing to yourself. In that case, no, I'm not looking at this entry. I'm looking at the entire row and the entire column. So, to be clear, if here I have Y and here there is a 1, it means that I have a link going from X to Y. If here there is a 1, it means I have a link pointing to Y from Y to X. So I'm just writing this. Now, since the sum is on the Y's, and the Y is the row index, it means that I'm considering column X of this matrix, right? So column X of this matrix. Why there is a T here? Because you cannot multiply a column vector times column vector. You have to transpose. And this is a transposition. Now, what happens if I want to know how age depends on A? You just look at this, right? You just look at this, and you will conclude that, well, actually, it's not much of a difference. You just remove the X here, and you will have the entire matrix. So, before you write further, this was just to give you an intuition of this process. So the new value of the hub vector is computed from the old value of the authoritative vector, and the new value of the authority vector is computed from the last vector of hubs that I computed. And you go on. What is happening to this process? Is it converging? Is it converging?
I have one question.
Yeah.
So why raise on y in the first sum? So, so there is a.
This one?
Now in the one under.
Here?
Yeah. There is a y.
It must have slipped. Must have slipped, I don't know. It was there, I cancelled something and it remained. I don't know why. So I just wanted to confuse you. Okay? So now let us try to make this. This looks like an iterative process. I mean, it has some resemblance to PageRank computation and the power method. You remember? The difference here is that I'm not computing a new, the new vector directly from the old one, the new hub vector directly from the old one, and the same from the authorities. I'm doing this 2 steps calculation. So, is this going to converge? You have to bet your money here. Yeah, to put your money here. Is this going to converge or not? Depends. Which is always a very smart answer. Depends. You know? We are winning. So, well, in order to understand whether or not it's going to depend, you remember the power method, right? We were able to find out when it is going to converge, how fast, and so on. Well, we didn't compute how fast, but we could have done that. We saw that there is these eigenvalues, you know? They decide everything. In this case, eigenvalues. Boo. Where are they hidden? I mean, yeah, sure, A has eigenvalues. It's a matrix, it's a square matrix. It will have some decomposition. In general, this is not a symmetric matrix. You see that? Well, the graph is directed. So the matrix needs not be symmetric. Not being symmetric is always a problem because decomposing a matrix that is not symmetric, you get non-orthogonal bases, a lot of stuff that you would like to avoid. We will be lucky, though. Well, actually, there is a trick hidden here. So, to make sense out of this, we had to elaborate a little bit on this, on the algorithm, and to see what is actually hidden in these 2 equations, because there is something hidden here. In order to understand what is hidden, we had to introduce a notion of time explicitly. So, you see here there is a notion of time. First I compute something and then I can compute something else, right? So there seems to be a notion of time. So let's try to make it explicit. What am I computing first? You know, the egg or the chicken? Well, what am I beginning with? Let's see, what am I beginning with? Actually, it is not really important, but you should begin with something and then be consistent. Okay? That's the only important thing. So let's say that you start to compute, for example, scores, then hub, then scores, then hub, and so on. Is this what I did? Well, I think it is what I did. Yep. So, yes. Okay, can I? So let us say that you begin as we have seen in the algorithm. So you have initial scores. So you have an initial vector of hubs, for example. You compute authorities, then you go back, compute new values for the scores, for the hubs, and so on. Flip-flop. So how can we do this? How can we represent this? So in general, it seems that we have some hub vector at some round t minus 1, and from the vector of hubs at round t minus 1, we compute a new vector of authorities at time t, at round t. Is that clear? We begin at time 0 with a vector of hubs. What is the vector of hubs at time 0? It's just a vector of ones, because every page has one vote, right? That's exactly what we did here, actually what we did here. You have a vector of hubs that is initialized to a vector of ones, and then these ones flow into their destinations, right? So you begin, you can say that, for example, the vector of ones. And then in the generic step, so for no. What did I do? I think I did the opposite. Very smart. Yeah, really very smart, Mr. Becchetti. Anyway, I guess it is the same. If it is not the same, I'll be wrong, and I will have to start from scratch. So don't take notes now. So, now, then, what did we do? Once we have computed the new vector of authorities, so the vector of authorities at time 1, we propagate this back and we compute the vector of hubs at time 1. So every round is 2 steps. First step, compute authorities. Second step, compute hubs. So the vector of hubs at time t yeah? Okay. So if we had started from authorities, it's not much of a difference. We would have set the authorities to, I don't know, 1. We would have propagated them back, and then force and so on. Okay? We would get similar equations. The main difference would be that in that case, AT is equal to ATHT, while HT is equal to AAT minus 1. Eventually, this will not change much. Now I have these 2 nice equations. And I notice something. I notice that this is the same time step, right? So what does it mean? Haha. This is true for every t, right? So this is also true for t minus 1. So I can say that ht minus 1 is equal to AT minus 1, right? Yeah? I mean, for every time step, this is true. So also, it was also true in the previous step. You know what? Let's try to plug it here, and let's see what happens. Haha. We almost got it. Now there is a direct dependence between the authority vector at time step t and its value at time step t minus 1. What can I now do? Well, now it's not that hard, I guess. Well, I hope. Yes, of course. Because now I will just replace, I will just take this and plug it here. Yeah, and what do I get? Okay? So, what I get are the following two beautiful equations. Okay? Now, these two equations have their own lives. Apparently, they proceed independently of each other. That's not true. Of course, they depend from each other. So you see here, they are depending on each other. But this is still true here because the matrix stays the same. Okay, so the evolutions of these two vectors will be depending on each other. Only not in an obvious way. Now, is everything clear so far? Good. So if you want, this is the algorithm. This is how you would compute it in practice, because here you have a matrix vector multiplication. Here you have something, well, actually, we have to be honest. Here you also have a matrix vector multiplication, because at worst, I mean, this matrix you may compute once and for all. If the matrix is too large, use this. Okay? Either the matrix is not too large and then you can proceed with these two equations in parallel, or the matrix is too large, you don't compute the product of the matrix by its transpose, and you just use this directly. Okay? Which again means accessing the disk, looking at the rows, you know. If this is on disk, it's an adjacency graph. So actually, we are, as you may have understood by now, very seldom are we computing matrix. Are we computing products between matrices? Never. Very often we are scanning a disk and just checking an adjacency list. That's it. So now we have this. Now we can go back to eigenvalues and eigenvectors. Yeah? So I repeat my question. Is this going to converge? Now your money there. What do you think? So first of all, I said before that the matrix A in general is not symmetric. Are these two matrices symmetric or not? Are they symmetric or not? No? Let's see. How do you decide that the matrix is symmetric? You see if its transpose is the matrix itself. Right. Is this matrix symmetric or not? The transpose of the product of two matrices. You remember? Invert the matrices and change the transposition. Good. ATA. So this matrix is symmetric. And you can bet your money that this is also symmetric. Are they the same matrix? No, they are not. Okay, so in general, ATA is not AAT. Okay? This is a general misconception. Each of these two matrices is symmetric, but it's not the same as the other. Otherwise, it would not be symmetric, by the way. Okay? So these two matrices are symmetric. Why is that so important? Because whenever you have a symmetric matrix, it has very nice properties. there is an eigendecomposition which is not Jordan decomposition, to be clear. A very simple one, in which the basis of the eigenvectors is orthogonal. You have orthonormal eigenvector basis, which is the maximum you may want from life, from algebraic life. Okay? So I'm not going to make it too long here, but what I wanted to say is that this matrix actually has nice properties. You can consider its eigenvalue decomposition, which has a very simple form. Actually, for example, ATA will be in this case, these are eigenvectors, so these are vectors. All these vectors are mutually orthogonal. So if you take the product between ui and uj, whenever j is different from I, you get 0. While the product between of this value, of this eigenvector by itself, of course, is the square norm of the vector. And these values here, they are always non-negative. Okay? Very nice. So they have a physical meaning, everything. I have not proven this. It's just a statement without a proof. But actually, the proof is not too terrible. So once you have this, you can do the following. You can say, well, in the end, what is this? This is the power method, right? Again, the power method only applied to this matrix. You see that? It's the power method. Only the matrix. You remember the power method? This is the power method, right? Well, it's P. Don't stick on the names. It's always a matrix. It's an n, it's a square matrix. So, the power method, when is it going to converge? Well, you have to look at the eigenvalues. Let's say if there is a gap between the largest eigenvalue in modulus and the second largest always in modulo, this is going to converge. Okay? It is going to converge to essentially the eigenvector to the component here, to this. This is a matrix. You see that this is a matrix? It's a square matrix. Essentially, over time, this is going to converge. If you take the repeated powers of this matrix, this is going to converge to the matrix that corresponds to the largest value that you have here. Okay? That will be the most important component over time. So this method is always going to converge, unless something bad happens. For example, actually, it's essentially going to converge. If you have just one eigenvalue which is the largest, it's maybe better. It's an easier meaning. It has an easier meaning. But otherwise, something is anyway going to converge. Okay? In this case. So eventually, over time, this stuff will tend to two vectors. Let's call them A and H without time, that represent the fixed points of this method. So there is only one caveat here. From the way we have defined this, the norms of these vectors can grow over time, so they can become larger and larger than 1. You see that? So, is this going to be a mess? I mean, convergence is always there. It is just a consequence of the power method, of the spectral structure of the matrix. What happens is that the entries are getting larger, or those vectors are getting larger and larger, even though they are stabilizing over time. And very often you want to avoid that. For that reason, the method typically is not exactly this, but it is this. Okay, so after every iteration you normalize so that the two norm of the vector of the authority or hub vector at time t is 1. Numerical stability, nothing more. Okay? When should I stop? Well, normally you stop whenever, actually it is written somewhere. That's essentially equivalent to what I wrote here. Why do they? Why are the entries 1 divided square root of n? Because if you take the 2 norm, is 1. Okay? If n is the number of components, you take the sum of the squares, you get 1. That's the reason. What is convergence criterion? Could be that the 2 norm, or the vector of the authority and hub vectors that you have not changed much, according to some parameter epsilon. That's all. Okay? So I'm not being rigorous. There would be a few things to prove, for example, that if you do normalization, it is the same as not doing normalization, convergence is ensured, and so on, but it's actually something that can be proven, and the real idea was the one I gave you here. So that's the real important one, because it's intuitive and you know already the power method. All the rest can be, let's say intuitively, if you normalize, things are not getting worse than if you don't normalize. Okay? Is there more to say? Well, actually, that's it. There is a number of issues. No, first of all, before the issues, have you got any questions on this so far? I'm not expecting theorems. I hope you believe me when I say, well, this matrix is symmetric, and you should not believe me. You should be aware that they are both symmetric. You should be aware that they are not the same in general. But you may believe me when I say that since the matrix is symmetric, it has an eigendecomposition with a family of orthonormal eigenvectors. That you can believe me. And you can also believe me when I say that all the eigenvalues of this matrix or this matrix, well, the eigenvalues of this matrix and this matrix are the same, because this matrix is just a transpose of this, so they have the same eigenvalues, not eigenvectors, eigenvalues. And they are all non-negative. All of them are non-negative. This can be proven easily, but I don't want to prove it. I mean, you don't need it now. Okay? Those are the important things to remember. Otherwise, this is the method. And over time, you're getting two nice vectors that gives you authority and hubness scores for your pages. Okay? So, what is, well, existence and uniqueness? Are those vectors? That's something that we considered when speaking of PageRank. Why should this, let's say, convergence be unique? Well, actually, you could think of the eigendecomposition and convince yourselves that it has to converge to the components, to the projector that corresponds to the largest eigenvalue because they are all non-negative. But in general, why uniqueness? Well, actually, these two vectors are special cases, actually are related to the left and right singular vectors. Maybe you never heard of singular vectors, doesn't matter. But they are related to a spectral decomposition of a matrix A that you normally never see in any algebra course, and which is a pity, which is called singular value decomposition, that always exists for every matrix and is unique. That's the reason. Okay? And singular values, singular vectors, are actually the eigenvectors of this matrix and of this matrix, because they are not the same. So It's just some anticipation, just to explain why the uniqueness should be the case. So actually, this gives a very precise meaning to hubs and authorities, because singular value decomposition is one of the main algebraic tools that are used to make sense of data. So to understand what the data are about, to understand the classes of the data. Huh? Okay? So if you have a collection of documents represented as vectors and you want to uncover the topics, one of the ways in which you can do this is applying a singular value decomposition. And roughly, every singular vector will be a description in some reduced space of the topic of the document. Okay? So in some sense, here you are converging to the main singular vectors of this matrix, of the matrix A, which give you the main topic in two perspectives. In this case, the main topics seem to be which are the most important pages and which are the pages that are pointing to the most important pages. Okay, these are the two main topics. I mean, the same topic, importance, seen from a different perspectives. The pages that are important and the pages that are pointing to them. That's the meaning. Well, apply until you have some convergence. And as you may notice, it is not, you can have high hubness, lower authority, and vice versa. Okay? So not all good hubs are good authorities, and vice versa. Okay? So, there is one question. These two algorithms were proposed roughly at the same time. Then, one resulted in a company that is worth the GDP of a country, and the other resulted in a very nice position in a top US university. So fame and a very good academic position. Why? So actually, it is not that PageRank is better than HITS, not necessarily. Actually, there are even search engines that are based on this idea. There are variants of this algorithm. And actually, these algorithm and its variants are sometimes used to process graphs, to uncover, to analyze the structure of graphs. So this algorithm is very useful. Why were the destinies so different? The main reason is the following, that with PageRank, you compute PageRank once and for all. You take the web graph and you give it a score, which is going to stay for the rest of your life. Doing the same with HITS is not that trivial, at least in the form that the algorithm was proposed initially. So the initial idea was the following. If you have a query submitted to a search engine, I will take the query, use a text, you know it was 1998, text-based search engines. I pick a collection of relevant documents for that query, were relevant according to text. Okay? I pick all the pages, or a bunch of the pages that are relevant for the document, and I have a small subgraph. Then I take this subgraph and add pages that are pointing to these pages, enlarge it a little bit, and then I apply this algorithm on that graph. Okay, this was the idea. But then this made the algorithm query dependent. You see why? Because for every query, you should extract the graph, compute, apply this algorithm. That is not something that is going to work in practice. You see? Beautiful idea. Won't work in practice. That was the reason, the main reason. Okay? What else? That's it for the moment about HITS. You will run into this or similar stuff again. Now, I have just some little time left, and I would like to spend it quickly on some related ideas. Whenever you speak about web search, you speak about spamming. Everywhere. When you speak about fake news, what is that? Spamming. It's a form of spamming, right? So spamming is pervasive. And you fight it. Which means that you try to distill quality from pages. Sometimes the problem is that according to just relevance-based scores, a spam page could be relevant. You can do, yeah. For example, you copy, you do cloaking, what is called cloaking. Cloaking. Cloak. Yeah, it's still done today. You just have a shoe shop, online shoe shop. You take the word movie or you copy a very important page about movies. You copy the text, paste the text, use the same color as the background, and you have a very relevant pages for movies as well. So I'm looking for a movie and I get shoes, okay? That was pervasively done in the past. But of course, then you have links, because those devils come up with link analysis, and then, then I have to find some countermeasure. If you have, then you have the second round. So you create link structures that will contribute to increasing your PageRank score. How do you do that? You use link farms. You automatically build up 1 million pages that will point to the same target page, for example, or you create more complicated structures. One question is it going to work or not? Let's see. This one case which was realistic years back, and that gives you an idea of why link spamming might work. So you have your target page. So this is the domain that you spammer control. The total number of pages that you can generate is M, millions. This is the entire web. The accessible web. Then you have your target page, the page you want to boost, so your shoe page, your shoe homepage. How can you do? Well, you build such a structure, and then you wonder, what is the PageRank of page T? You try to estimate the PageRank of page T so that you get an idea of, for example, how the PageRank of page T depends on the number of pages that link to it. Who knows? So, fortunately, they did the analysis for me. What is going to happen? Well, let's say that the target page has PageRank, let Y be the PageRank of page T, and let X be the overall PageRank contributed from accessible pages. So these are other pages in the web that do not belong to the link farm. Maybe they will also point to you. Some of them will. And they will contribute a total PageRank score X. If you are just a spammer, you know, porn, casino, and so on, this may be 0, or very close to 0. That's why, so your entire rank will come from your farming structure. So what is going to happen? First of all, what is the rank of a farm page, or one of these pages? You see the doubly linked structure? So you have a link going from every page in the link farm to T and vice versa. That's important. It should be vice versa. Because in that way, it becomes a self-reinforcing relationship. Why? Because if T happens to have some links from outside, by having T point to every other page M, you will deliver this flow of PageRank also to the farm pages, and they will send it back to you. You see the point? So, what is the rank of every farm page? Well, since every front page is only pointed to by page t, it will be beta times the rank of y divided m. You agree? Divided m because it has odd degree m. Plus this score which is always there. What is the page rank of y? The page rank of y is equal to the contribution it gets from outside plus beta m times its page rank, which we have computed before. Notice that this has to be true at the equilibrium, at the stationary distribution, plus 1 minus beta over n, which gives you this. I mean, you trust the math. I did it once and that seemed to be correct. So we just trust the calculations. You get this. At this point, you have an equation. So you can express y as a function of the rest. If you do this, you get this expression, where c is a constant, which happens to be close to 1. Well, not close to 1. Close to 1 over 1/2. Close to 1/2, because beta is 0.8, 0.85, 0.9. So, what does it mean? It means that your page rank, the page rank of y, is essentially the true page rank it should get from the other pages, because this is 1 minus beta square, so it's a bit less than 1/2. You see? It's roughly, this is a constant time x, okay? So having this link structure boosts the page rank that you get from the rest by some factor which is in the order of 1 over 2. But then there is this term. This term crucially depends on m. So it increases linearly with m. So if you increase the number of your farm pages by a factor 10, this term is increasing by 10 times. So it seems to be a good bargain. You see? Okay? So you have an incentive. Since generating a new page is not much effort today, you generate it automatically, right? You do not have to have people typing the web page. It seems to be good business. So that is why it is very important to identify spam pages, or at least to demote spam pages, so to discourage spammers from having spam pages. Okay? How can you do this? Well, fighting web spam means, in particular link spam, means identifying web spam pages, first of all. Okay? And then punishing them. Of course, you are not going to do this page per page, because this is like, so you have an algorithm that does this. So they come up with an algorithm, and your countermeasure is another algorithm, or a suite of algorithms. And it's fun. I mean, computer scientists have fun this way, you know? Just, you just play games. So, which is the type of tools that we can use? I'm just giving you an example, a high-level idea of an example in the next few slides. There are many other ways of doing this, based on different ideas. This one is one of the closest one to the original idea of PageRank, and it is the following. Assume that for some reason I can identify a sufficiently large subset of authoritative pages, so high-quality pages. Why would that be the case? Well, because actually you know that, for example, Wikipedia pages tend to be authoritative, high quality. So then you have these directories like dmods, which contain authoritative material. And then maybe the most prominent newspapers, regardless of their viewpoints, I mean, they are authoritative sources, mostly, and so on. So you can come up with a large number of high-quality pages. And you can actually retrieve them automatically also, right? I mean, you do not have to do this by hand. So, what is the idea? Assume that I have a subset of seed pages, which I call the good pages. I know that they are trusted pages. I trust they have high quality contents, no matter what these pages are about. They are high quality pages. And then, essentially, what I do will be to perform topic sensitive PageRank using the seed of good pages as a seed. You see that? Is it clear? Yes or no? We have seen topic sensitive PageRank last Monday. You just do topic sensitive PageRank, only your personalization vector P will be, how can we, sorry, let's say 1 over S. Where S is the subset of good pages. You can have another distribution here, as long as it puts 0 mass on non-good pages, on all other pages. So you do topic-sensitive PageRank. Teleporting, and then you have a ranking, right? And then you say, okay, this is a measure of, let's say, the quality of the pages. So it's a positive measure of the quality of the pages. At that point, you have to find out, identify spammers. Trivial way, decide a threshold. Whenever the threshold, in this case, the trust rank, it is called trust rank, is too low, the page is spam. Brutal, that's very simple, a bit simplistic perhaps. And also because you have an absolute measure of spamness, which is the same for all pages. That may not be a good idea. So you can come up perhaps with a better idea. But I mean, this makes sense. A slightly different idea is the following. Every page has 1 unit of money, and it can share this money across different pages. Okay, so every good page, so every page in the set S has initially a unit of money, which it can spread like PageRank, the very same way. So essentially, this is just to tell that the trust rank algorithm by Giongi and Garcia Molina was actually initially conceived in this form. It is not exactly a topic-sensitive PageRank, but rather every page has a unit, let's say, of money or whatever, and then you spread this unit, this vote, across the outgoing links, and so on. Okay? So up to a factor of trust rank and PageRank with, and personalized PageRank with good pages as teleporting is the same. Now there is the other issue. Instead of using a hard threshold to decide what is spam and what is not, try to use something a little bit, well, that is why it is going to work. I mean, why it could be a good idea. Hey, that's the last thing I want to say. Good. So, what is a better solution to decide what is spam and what is not? On one hand, you would have PageRank, right? For every page, you have a PageRank score. On the other hand, if you apply this idea, for every page, you will also have a trust rank score, okay? So the idea is the following. When your PageRank is consistent with your trust rank, essentially, you're likely to be a good page. Otherwise, if there is too high an imbalance between your PageRank and your trust rank, maybe you should be punished a little bit. So they came with this idea of measuring what is called spam mass. How is it defined? This is trust rank, essentially. So PageRank computing using good pages as teleporting set. And this is the standard PageRank. They are both two distributions. They sum to 1. All the entries sum to 1, so you can take their difference. I am not saying that if you write the quotients and take the difference, you get exactly this. I'm just saying that these are two distributions and you can take their difference. Okay? So for every page, P, you will compute what is called the spamicity of a page as the difference between the value, your value of PageRank and your value of trust rank. Okay? So this difference can be positive or negative, right? If it is negative, what does it mean? It means actually that PageRank, so that your quality is higher than estimated in PageRank probably, or maybe my seed set is not large enough, if you want. Okay? Instead, if this difference is highly positive, it means that most of your trust rank, most of your PageRank is not originating from those pages probably, but from other pages. So there are two possibilities. Either I was not good in picking that set, so it is too small, for example. Or I was good in picking that set and you are a spammer. In both cases, I define this ratio. Whenever the ratio is highly positive, I say that you're a spammer. So this is the spam mass of a page. They define it in this way. Why exactly in this way? Well, it seems to work in practice. Okay? I mean, you try several combinations and, this works. Okay, no deep math here. There is some math here, but not there. Which problems do we have to solve? Yeah, well, picking S. What is a good seed set? So we have two conflicting objectives. The first objective is that S should be very large. So ideally, S should be the entire set of high-quality pages, right? The larger, the better. The problem is that doing this requires humans at some point. And you pay humans, and they are slow. So you have to do this automatically to some extent. First way, pick the top K pages of PageRank. Why? The idea is that if a page is really at the top, it cannot be a low-quality page. Or the entire PageRank idea would be wrong. Makes sense. There have been some notable exceptions, some notable hacking of PageRanks in the past, but this is generally true. K has to be as large as possible, of course. Another way, use trusted domains. dmods, .edu, gov, and so on. Okay? I think I'll stop it here. Yeah, I'll stop it here for today. Also because I'm finished with this part. So, and I have 2 kids to pick, so I have to rush. And I think next week you will enjoy the company of my big friend. So, have fun with him.